Welcome to the live interaction session for the course Semiconductor Device Modeling and Simulation. This is week 11. I will introduce myself first. I am Ananya, a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. I will be the TA for this session. People can join in the meantime, but I'm recording the session so that it is available for everyone. I will start now. Okay, I will discuss some of the problems related to the topics those were discussed in this week 11, mainly quantum mechanics and Schrodinger's equation. So this is week 11. Let me write down the first question. The question is, which of the following is true for Schrodinger equation? So the options are A. It is a classical equation that describes the motion of particles. It is A. Classical equation that describes the motion of particles. Option B is, it is a relativistic equation that includes the effect of special relativity. It is a relativistic equation that includes the effects of special relativity. Option C is, it is a quantum mechanical equation that describes the behavior of particles. Last option D is, it is an equation that is only applicable to particles in vacuum. So what will be the answer for this? Answer for this question is option C. It is a quantum mechanical equation that describes the behavior of particles. So the time independent Schrodinger equation is so this equation is given as minus h bar square by twice m. If I write it in only in one dimension, so the like the wave function is position dependent, but I'm only considering only x direction, so that will be del 2 by del x2 psi x. It is also a, so let me write down time dependent. Okay, so wave function is x and t, so it is position and time dependent plus vxt. So this is the potential, and then psi xt is equal to E psi, energy into psi. So this is written as using quantum mechanical operator. So this is IH bar del LT of psi xt. So this is time dependent Schrodinger equation, and then we can separate these two out. The time independent part, so that is what we are more familiar with. So we can separate the wave functions out. This is the general time dependent equation, Schrodinger equation. Now the solution of this equation is the wave function psi xt, and it gives information about the particles, okay, for which we are using this equation. Okay, the solution of this equation is psi of xt, which is known as wave function. Here in this course we write this equation for electron, so this is the wave function that describes the electron, and the wave function contains information about the particles. So this is the first question. Let me check the meeting also if everything is fine, because no one is in the meeting, so it is very difficult to say if there is anything wrong. let's go to the next question. Question 2. Let me write down the question first. The quantized value of energy of a particle in a box is given by so what is the quantized value of energy of a particle in a box? The options are A, energy E equal to h square by 8 ml square, nx square, ny square plus nz square. Option B is E equal to nx square plus ny square plus nz square. Option C is n equal to 1 by 8 into 4 pi by 3 n cube. So it should be E. Okay. Option D is E equal to h square by 4 m l square nx square plus ny square plus nz square. So this is the question. I have discussed one question, so I'm going to the next question, question 2. This is the question. The quantized value of energy of a particle in a box is given by. So the options are given. I will solve the question. You can try to solve it along with me. So what is given? It is a particle, a quantum mechanical particle in a box. Now I will solve this question in 1D, but you can extend this to 3D also. Okay, first in 1D, instead of a box, I will consider a potential well. So the diagram is not like very clear, but you can get an idea. So this is a potential well. So here the potential Vx goes to infinity at this point, and here also goes to infinity, and inside the well potential is 0. This is x equal to 0. I am considering 1D, only x direction, and this is x equal to L. Now basically we will solve this Schrodinger equation inside the potential well, which is kind of similar like solving the equation inside of a box. Okay. Now the time independent Schrodinger equation, I'll just write S E, okay, that will be minus h bar square by twice m d2 psi by dx2 equal to E psi. Because I'm considering time independent and I'm only considering 1D, so that is why I'm taking the derivative like this, not partial derivative. Now the solution for this equation will be, this kind of differential equation will be so in some form of cos and sine. So we will write psi wave function as a sine kx plus b cos kx. Okay. This the solution for this kind of differential equation we studied in some maths courses. So the format for the solution will be like this, directly giving you that. Now there are few unknown terms a and b, and also we have to apply the boundary conditions so that the boundary conditions are satisfied. Now because the potentials are infinite at this position, so the particle will be inside this potential well, not outside of the well. That means psi here goes to 0, this is also goes to 0. So these are our boundary conditions and we will apply that. So the boundary conditions are so at x equal to 0, our psi x should be 0. Okay, that means psi x at 0 plus this should be equal to psi x at 0 minus. Okay, so we will put x equal to 0 in this equation, so this will be b of cos 0 will be equal to 0. So this is b equal to 0. Is there any question? Yes, this is semiconductor device modeling and simulation. So this is for week 11. So the course, the topics those were covered here, mainly the quantum mechanics part, so that is why I am discussing problems related to those topics. Okay. So this part is basically 0. Now we will apply the second boundary condition. So wave function is also 0 after x like greater than L. So at the boundary also we should apply the boundary condition, that is psi x equal at x equal to L, the wave function is 0. So at x equal to L, psi of L will be 0. That means psi of L plus is equal to psi of L minus, which is 0, because psi of L plus, if I am considering if this is a positive x direction, so psi of L plus is actually 0, so that is why psi of L minus, that is inside the well, will also the wave function will be 0. So already this part is 0, so that is a sine KL is equal to 0. Okay. Now if a equal to 0, then this wave function, so this solution will be like a trivial solution. That means everything is 0, right? But we know that there is a particle and there is a wave function that is associated with that particle. So a we don't write as 0, okay? If we write a equal to 0, then everything will be 0. But psi x is not 0, but psi x will be 0 with certain conditions, and the condition will be for this case, so sine of kl will be 0, okay, and this condition is satisfied when k and l is equal to n pi. Okay, here n is 1, 2, etc. Okay, so this is our wave function. You can solve what is the exact value of a. Okay, I will not go through this in this question, but I think that was discussed in the equation in the lectures also, and you will find in any like solid state device books. Okay. Now our question is to find the quantized value of energies. Okay. Now because of this kind of confinement, actually like when the particle is confined inside of a potential well or inside of a box, so the allowed energy levels will be quantized. And how the energy levels are quantized? So the energy is equal to energy E is given as, so we know that energy is some form of E square by twice m. So this is h bar square k square by twice m. Okay, so this will be h bar square k square by twice m. Now in this case k is not like a continuous, k is quantized, so n has certain values, so kn is also quantized. It is not a continuous variable, like continuous number. So this I can write as h bar square kn square by twice m. Because kn is not continuous, that is the particle cannot take any random k value, that is why the particle also cannot take any random energy. So the energy levels are quantized, and particle can take a particular energy level. Okay, so the energy level is not continuous. Now this will be h bar square by twice m, and for 1D case our kn is n pi, so kn will be n pi by l square. Okay, now this is for 1D. For 3D, so let's consider the part. So the box, the sides of the box are Lx, Ly and Lz. So basically it is a cube, all three are equal, and which is equal to L. Okay, if it is like that, then the quantized energy levels will be, you can solve similarly for 3D case also. The quantized energy levels will be h bar square by twice m, pi by L I am taking as common square, and instead of n, so this will be nx square plus ny square plus nz square. Okay, which is equal to n square. So n square is x square plus y square plus nz square. So it comes from because of the kx, ky and kz. Okay, so in the question it is given in terms of h square, Planck's constant, not h bar, so I will change it to that. So h bar square will be h square by 4 pi square. So h bar is h by 2 pi into twice m into pi square by L square. This is nx square plus ny square plus nz square. So this will be, this pi square get cancelled. So this is h square by 8m L square nx square plus ny square plus nz square. Now the particle will have different value of energies based on these numbers like nx, ny, nz, these quantum numbers. Okay, so this is the expression for quantized energy level in a 3D box. So the answer is A. E equal to h square by 8 ml square nx square plus ny square plus nz square. So if the box is very large, like the size of the box is very large, so then the energy will be small. So and also the separation between the energy levels will be small, like this separation will be very less. Okay. But if L is very small, that means the particle is confined within a very small volume, then energy levels will be far apart, and basically that is why the quantization is more prominent when the dimensions are much smaller. Okay, hope the question is clear. I'll go to the next question, question 3. So the question is, a 50 electron volt electron so 50 eV is the energy of the electron, approaches a square barrier the size of the square barrier or the height of the square barrier is 70 electron volt, and the thickness of the barrier is, so there are two options. First is 1 nanometer thick, and the second is 0.1 nanometer thick. The question is, what is the approximate probability that the electron will tunnel through? The options are 1.32 into 10 to the power minus 20. So the tunneling probability is very small, means 0.01. So this is for a thickness of 1 nanometer, first option, and second option is for 0.1 nanometer thick barrier. Option B is 6.83 into 10 to the power minus 15.1. Option C is 6.83 into 10 to the power minus 10.01. Option D is 6.83 into 10 to the power minus 5.3. Now the question is like this: suppose there is a barrier, you can consider it like a wall maybe, okay. So there is an electron here, it has certain energy which is 50 eV, but the height of this barrier is 70 eV. Now classically, if the electron has an energy which is smaller than the barrier height, then this electron cannot go to this side, right? But quantum mechanically, even though the energy of the electron is actually less than the barrier height, there is a non-zero probability that the electron can tunnel through this barrier. And we have to calculate the tunneling probability for two cases: when the barrier thickness is 1 nanometer and when it is 0.1 nanometer. Now just by looking at this number, we can say that the tunneling probability for the barrier with thickness 0.1 nanometer, this should be higher because it is like less thickness, whereas thicker barrier will be difficult to penetrate. So the tunneling probability will be less for the 1 nanometer thick barrier. So the tunneling probability for 1 nanometer will be less than tunneling probability for 0.1 nanometer. Okay. Now we have to determine the numbers. I hope the question is clear. I will go to the solution next. Okay. So how we will calculate the tunneling probability? So exact equation for the simple square barrier, what should be the tunneling probability, those can be calculated. I think those were also discussed in the lectures, but I will not go through those are already discussed. I will use an approximation because the question is to calculate the approximate probability. Now to calculate approximate probability, we can use WKB approximation. So WKB approximation is used in this kind of barrier, okay. So even if the barrier is looks something like that, these also we can use WKB approximation if this variation is not large. And another thing is that this approximation is used when the tunneling probability is actually very small, okay. I will use that. this approximation, as I mentioned earlier, it is valid when tunneling probability is very less than 1. So maximum tunneling probability is 1. If it is very less than 1, then we use this approximation. Now so our barrier is constant, there is no no variation, it is a square barrier. This is V naught, okay, which is for us 70 eV. Let's consider this thickness of the barrier as A. Now electron is here, so this is region 1, this is region 2, and this is region 3. Let's consider the wave vectors. In this region will be k1, here this will be also k1 because energies are same, energy and wave vectors are related, and in this region it is k2. Let's see. Now for constant barrier, so in WKB approximation we define a parameter called gamma, okay. So for constant barrier, that will be so this is 1 by h bar integration of 0 to a, okay, this thickness, mode of 2m. This is actually Vx minus energy of the particle, it is an electron for our case, dx. Now for us Vx is constant, so the problem becomes easier. So this is 1 by h bar integration of 0 to a root over twice m v naught minus e dx. So this will be 1 by h bar root over twice m v naught minus e a, okay. So this is this has some form like alpha into a, so that is this gamma, or anyway this gamma is using this gamma we will calculate tunneling probability. That depends on the thickness of the barrier, okay. Now how the transmission probability is defined in WKB approximation using gamma. So the expression is TE is equal to exponential minus 2 alpha A. Okay. Basically in WKB approximation, transmission probability TE has a form exponential minus 2 gamma. Okay. Now what are given? So given E is 50 eV, V naught is 70 eV. Okay. So we will calculate for two cases for two values of A. Okay. So the first case A is barrier of thickness 1 nanometer. I think it is 1 nanometer. So that means A is equal to 1 nanometer. Okay. So our alpha will be, which is 1 by h bar root over twice m v naught minus e. Okay. So this will be square root of 2. Let's consider the mass of free electron because no other information is given. So this is 9.11 into 10 to the power minus 31 kg. Now V0 minus E is 70 minus 50, so that is 20 EV. But I will write it in terms of joule, because I have to do the dimensional analysis, because this is kg. H bar, the unit for H bar is joule second, so I'll write this also in terms of joule, okay, so that I can cancel out, or basically I can match the dimension. So this is 20 into 1.6 into 10 to the power minus 19. So this is joule, which is kg meter square second to the power minus 2. If you don't do this conversion, then the answer will be wrong. This is divided by h bar, which is h by 2 pi. So h is Planck's constant, 6.626 into 10 to the power minus 34 by 2 into 3.14, and this is joule second, so that will be kg meter square second to the power minus 1. Okay. So this will be, let me calculate. So this is 2.288 into 10 to the power 10. So the unit will be kg, will get cancelled. So here this will be kg meter second to the power minus 1, and from here this will be kg meter square second to the power minus 1. So the unit will be meter inverse, right? Which is the correct unit? We will see just here. So the transmission probability is exponential minus 2 into, so that it is 1 nanometer. So let me write it here, 22.88 into 10 to the power 10 into 1 into 10 to the power minus 9. Okay, so this is alpha, this is A, this is okay. So these two will get cancelled, and the tunneling probability will be so TE is 1.33 into 10 to the power minus 20. This is for thickness of 1 nanometer. We have to do that for the thickness of 0.1 nanometer. So here you can see the unit here is meter inverse, this is meter, so this get cancelled, and the probability we finally got as this term, which is unitless. Okay. it's A equal to 0.1 into 10 to the power minus 9. So the tunneling probability will be exponential minus 2 alpha A, which is exponential minus 2 into will I get right? 0.1 into 10 to the power minus 9 again, and there will be no unit, and this will be so this is 0.0103. So as I mentioned earlier, that the tunneling probability for thicker barrier will be less, so this value is very small compared to this, and you can see the order of difference. So this is 10 to the power minus 20. If the thickness of the barrier is kind of large or comparable to few nanometer, then the tunneling probability is almost equal to 0. So that is why these phenomena tunneling is not observed like for in case of like classical system, only observed in quantum systems where the dimensions are very small. Now these are the calculation for tunneling probability. So these are approximate calculation. So this is like very close to the actual tunneling probabilities, but you can instead of using WKB approximation, you can actually solve for tunneling probability. What is the expression for tunneling probability for this kind of a barrier, because it is a very simple case like a square barrier. You can calculate the tunneling probabilities by solving this Schrodinger equation in all three regions, and then applying the boundary conditions at this x equal to 0 say, and x equal to a, or whatever the way you want. Maybe you can take the x equal to 0 here in the middle. Okay, this is, you can take x equal to 0, this will be a by 2, this will be minus a by 2, and then you can solve the system. So this will be a one-day system. Now do we have the answers in the option? So the first is 1.33 into 10 to the power minus 20, and then 0.01. So our option is option A. Our answer is option A. I hope the question is clear. If you have any question, if you cannot unmute, then you can write in the chat box also. So I'll go to the next question. So the question is, a quantum well structure is made by sandwiching a 20 nanometer gallium arsenide between two aluminum arsenide barriers. Each of thickness 50 nanometer. The effective mass of electrons in the well is 0.067 times the mass of free electron. Determine the approximate energy of first excited state. The options are A 56.3 MeV milli electron volt, option B is 48.1 MeV, option C is 0.9 eV, option D is 1.9 eV. So the question is on quantum well structure. So this is a numerical, but the concept is same as we discussed in the second question. Like this. So this is a quantum well. Okay. So we will use this expression basically, but the question is on 1D, like it is a quantum well, so it is a 1D case, but the expression for energy will be something like this. So what is this? So this is like gallium arsenide and aluminum arsenide. Those materials are connected back to back. So the structure is like this. So this is aluminum arsenide, this is gallium arsenide, this is again aluminum arsenide. Okay. So the band diagram, because of the different band gap for this material, so the final band diagram will be something like this. Say this is the conduction band edge maybe. Okay. So this is like maybe easy. I'm not sure about the band gap or the difference between the band gap for aluminum arsenide and gallium arsenide, but this is like a typical scenario for quantum well in general. Because of the different band gaps, say if a material has a band gap something like this and another material has a band gap like this, if you connect this, so there will be a formation like this kind of band gap, right? So this is like a quantum well. So in the scenario given in the question is something like this. So these materials are gallium arsenide material is sandwiched between these aluminum arsenide material and the thickness of these layer, gallium arsenide layer, is given as 20 nanometer. Okay, so that is basically our width of the potential well, width of the quantum well here. Okay, now we have to calculate the energy of the electrons here in this region. Okay. Now the expression is known. You can check the lecture notes or any book. The expression for energy of a particle inside a 1D potential well. So the expression is I have also solved in the question 2. Okay, energy of particle inside a 1D potential well. So this is En is equal to n square per square pi square by 2ml square. Okay. So this is equal to n square h square by 8 ml square. Okay. Now n varies from 1, 2 and so on. These are the quantum numbers. Here n equal to 1 means the ground state. Okay. The question is given as, so here En is energy of nth level, and you know the other parameters. H bar is Planck's constant, so H bar is 1.06 into 10 to the power minus 34 joules second. Here I will use the m star instead of m, because we have to consider the effect of the material, because it is given as gallium arsenide. So here we should use the effective mass of electron for gallium arsenide. So m star is given, effective mass is 0.067 m naught. M naught is the rest mass of electron, which is 9.11 into 10 to the power minus 31 kg. Standing question. The topics are covered, so that is why I'm covering these kind of questions. So I think in the assignments also similar questions will be there, and about like how many people are there in the min. So right now there are not people like there are not many people, like you are the only one, but I upload these recordings, so I don't know how many people actually watch those. Okay. Please. Okay. You can see in the assignments, so consider an electron 1D infinite potential well of it. So there are questions for 1D potential well. So this kind of questions will help you to solve these questions. Please sure. And about the exam, so I have never seen the exam question paper, so but it should be similar, like the topics will be same, those were covered, right? So these topics are already covered in week 11. Now the question is, we have to calculate the energy of first excited state. So as I mentioned, n equal to 1 is ground state, okay, and n equal to 2 will be our first excited state. So energy of first excited state will be if you know the expression you can calculate, like then the question is not very tough, but you have to understand here, like here it is mentioned the first excited state, so you should not calculate it directly by taking n equal to 1. Okay, so here E will be n square 2 square 6.626 into 10 to the power minus 34 square divided by 8. M star is 0.067 into 9.11 into 10 to the power minus 31 into L is 20 nanometer, so this is 20 into 10 to the power minus 9 square. Okay, so this is joule second, so this is joule second square, so this is kg meter square second to the power minus 1 whole square divided by this is kg meter square, right? So the unit will be kg meter square second to the power minus 2, which is the unit for joule. So this energy we are calculating will be in terms of joule, okay, but in the answers the options are given in terms of electron volt, so we have to do the conversion. Okay, so let's calculate it in terms of joule first. So this will be 4 into 6.626 into 10 to the power minus 34 square divided by 8 into 0.06. So the answer will be 8.99 into 10 to the power minus 21 joule. Now we will divide it by 1.6 into 10 to the power minus 19, okay, to get the answer in electron volt. So this will be 1.6 into minus 19. So this is 0.056 electron volt. So this is 56 milli electron volt. Now we should have this in the options, right? Yeah, here. So like you can calculate it to the decimal points that is given in the option. So answer here is A, 56.3 milli electron volt. I hope the question is clear. Like if you want you can refer to any book or lecture notes to to study about Schrodinger equation and the basic part here, that is the solution of Schrodinger equation and how to solve the boundary conditions in potential well. And then we can also study the transfer matrix method, that was also covered. Let's go to the next question. Let me check this. So the question is, which of the following is a key feature of a quantum correction model? Few statements are given in the options. So the first statement is, it applies only to classical systems. And cannot be used to analyze quantum system. Next statement is, or next option is, it assumes that all particles in the system are distinguishable and cannot be tracked individually. Next statement is, it incorporates the effects of quantum mechanics into classical statistical mechanics. option D is, it assumes that particles in the system are in thermal equilibrium and have Maxwell-Boltzmann distribution of energy. So the question is about quantum correction model. Here the answer is option C. It incorporates the effects of quantum mechanics into classical statistical calculations. So what are classical statistical calculations? The way we calculate the current transport using drift diffusion, or the way we use different distribution functions. Those are statistical mechanics. But when we are talking about very small dimensions, for example in nanometers say, then the quantum effects are like very prominent, and it is important to consider those effects. Like what can be the effect? For example, tunneling that we are discussing, right? If we have a very thin barrier, classically electrons cannot pass through this barrier, but quantum mechanically it can, because electrons have is also like, it has a wave particle duality, so it has a wave nature, and wave can penetrate through this. Okay, the amplitude will decay here, but there is a non-zero probability that it can penetrate through. So it is important to consider those effect, and in this quantum correction model, basically the classical calculations are done, like how the carriers move or electrons move, by considering quantum mechanics or considering the quantum effects. Okay. So in the current calculation, so what it is used, the transmission probability of electrons from one side to the other is also considered during the current calculations. Okay. So this is this question. Let me go to the next question. The wave function psi x, some expression is given for the wave function a exponential minus b square x square by 2. Okay. So the wave functions are generally written in terms of exponential or sine or cosine. Okay, so here a and b, so these are real constants. Okay. So this wave function is for a particle of mass m with energy E. Okay. So these are the information given. and the particle is in a wave function. So the particle is experiencing a potential Vx, okay, such that Vx equal to 0 at x equal to 0. Okay. So the question is, find the value for V in units of h square b square x square by m. Okay. This is h bar square. So the options are A 0.5, B 0.2, C 0.8, D 1. Okay. Now so basically, to solve this equation, again we will use Schrödinger equation. To solve any quantum mechanical problem, that is our first point. We have to consider the Schrödinger equation. So what is given? The wave function is given, which is psi x equal to a exponential minus b square x square by 2. The Schrödinger equation required the double derivative of the wave function. Okay, so we will do the derivation here first, the differentiation here first. So dψ by dx, this will be a exponential minus b square x square by 2. So this will be minus b square by 2 twice of x. Okay, that's cancelled. So minus b square x, and this is psi of x. The double derivative d2 psi by dx2 will be, so minus b square is constant, differentiation of this psi of x dx, differentiation of x with respect to x will be 1 plus x d psi by dx is minus b square x psi of x. Right. So this will be minus b square minus plus this is b square x whole square, so there are 2b square and x square, okay, and psi of x. So we have the double derivative of the wave function. Now we can write this Schrödinger equation. Okay, so this is question 6. Okay. So we'll write this Schrödinger equation using this. This is minus h bar square twice m d2 psi by dx2 plus v of x psi is equal to e of psi. So minus h bar square by twice m minus b square plus b square x whole square psi. Let me take this to the other side, so this will be e minus vx psi. Okay, so that means minus h bar square by twice m minus b square plus b square x whole square is equal to e minus vx. Okay. Now what is given in the question? The question is given that Vx is equal to 0 at x equal to 0. The potential is 0 at x equal to 0. That means the electron or the particle is not experiencing any kind of potential here at x equal to 0. So this is using from this expression. So this is minus h bar square by twice m minus b square is equal to E. So energy is equal to h bar square b square by twice m for this particular case. Okay. Now we have to write this Vx in terms of something similar to this. Now this is at particular x, that is at x equal to 0 in general. So energy will be so this part is basically energy, right? So this is E minus h bar square by twice m b square x whole square. This is equal to E minus Vx. Okay, that means Vx is equal to h bar square by twice m b square x whole square. So we have to write Vx in some form like this. Let me check. So we have to write h bar square b square x whole square by m. So let me take the half common, so that is 0.5. That will be exactly the part that is given in the question. So this is h bar square b square x square by m. Okay. So if I consider this as what should I consider? Let's say capital A maybe, and then no, this already A is also given. So let's say this is C. So this is like 0.5 into C. Okay. So our answer is A. Answer is A. So again I am saying that this is your starting point. Like if you want to solve this kind of question, start with Schrödinger equation. Let's go to the next question. The question is, consider a quantum well consisting of two materials with different band gaps. And the materials have band gaps such that the conduction band minima, so EC, of the wider band gap material is higher than the conduction band minima of the narrower band gap material. That means two semiconductors are connected and both of them have different band gaps. Okay. Now, if that is the case, which of the following statements is true about the energy levels of electrons in the quantum world? The options are the energy levels are continuous, and spread out over a range of energies. Next option is the energy levels are quantized and spread over a range of energies. Okay. Next option is the energy levels are quantized and confined to the narrower band gap material. Last option is option D. The energy levels are quantized. And are confined to the wider bandgap material. I will take a pause here so that you can read the question and think about it. What will be the correct statement? Okay. So this is a very simple question. If you have understood the concept of quantum will that I mentioned in some earlier question, maybe which questions in this question. So this is similar. Okay. The question is. Uh, Two materials are connected and they have different band gaps, and the EC of the wider band gap material is higher than the EC of the narrower band gap material. So what will be the band diagram, like how the band diagram will look? So the band diagram we draw with respect to the position, or with respect to the x-axis or y-axis. So how we will do that? We have two different materials, two semiconductors. So let's say this is material 1. This has a band diagram like this. This is EC, this is EV. I don't know whether it is a p-type, n-type or intrinsic, so let's not consider that, but it has a band gap, say EZ1. And we have another material 2. It has a different band gap. So this is EC, EV, and this is EG2. Okay. So this is our wider band gap semiconductor. And this is the narrower band gap. Now these two are connected in such a way that a quantum well is formed. Now how these materials are connected to form a quantum well? Let's say this is material 2. Then material 1 is connected. And then material 3. Material 2 again. So this will have a band diagram like this. So this part, if you look at it, it is like a quantum well. Okay. So if there is an electron here, this electron will be confined in this region unless it has energy which is higher than the this difference. And there will be energy states in this quantum well, and the energy states are quantized. So there will be discrete energy level, and the expression for energy will be E in terms of En, where n can be 1, 2, 3 other integer number. Okay, the expression for En I have already discussed. Now based on the energy of the electron, that it can take any energy value among these values, like among these energy levels. So when we connect the materials like this, we get a quantum well, and in that case the energy levels are quantized because of this confinement. Okay, because the electron is confined, that is why this quantization happens. Okay. This comes from directly from the solving by solving this Schrodinger equation, and because of this confinement we get like discrete energy level, as you can see from this diagram, discrete energy level in the material 1, that is in the narrower bandgap material. So what will be the correct answer for this? The energy levels are quantized first of all and confined in narrower bandgap material. So the correct answer is C. Here we can approximately like consider this potential well as a rectangular potential well, which is similar to like a infinite potential barrier. Okay. This is not exactly a real situation, but we can consider like this infinite potential well and rectangular well. This is not a realistic situation, but if we can have a combination of materials like this, we can get a similar kind of structure which we can solve using Schrodinger equation and by considering it as a potential value. I hope this question is clear. If there is no question, I will go to the next question. Let me write the question first. An electron is confined to a one-dimensional infinitely deep potential well of width L equal to 0.1 nanometer with zero potential at the bottom of the well. So this is basically like an infinite potential well, ideal infinite potential well scenario. Okay. The question is, what is the smallest amount of energy the electron can have? And because the material is not given, consider free electron mass. The options are A 37.7 eV, option B is 0 eV, option C is 3.7 eV, option D is 14.7 eV. So this is the question. Now we already have the expression for energy in a one-dimensional infinite potential well case. I'll use that. So this is one D potential well. Here it is infinite, here Vx is infinite, here V of x is 0. This is x direction, this is x equal to 0, this is x equal to L, and in the question it is given as L equal to 0.1 nanometer, equal to 0.1. Now for this kind of case, what is the quantized energy levels? E of n is equal to n square h square by 8 m L square, where n is equal to 1, 2, 3 and so on. Now here n equal to 1 means ground state, and that is the minimum energy that an electron can have inside a potential well, inside an infinite potential well. Now as we can see from this expression, it is non-zero. So even n equal to 1, En is non-zero. That means even in ground state inside of a well, the energy of an electron cannot go to 0. Okay, so this option is definitely not correct. So let's calculate what will be the correct answer, because we have to calculate the smallest amount of energy the electron can have, so that will be given by n equal to 1. Now E of 1 will be equal to h square, which is, so let me write, so this is 6.626 into 10 to the power minus 34 square. This is 8. M will be M naught. Okay. So this is 9.11 into 10 to the power minus 31. L square is, so this is 10 to the power minus 10, right? So this is 10 to the power minus 20. Again, I will do the dimensional analysis. I keep everything in terms of joule because it is easier to do that for the dimensional analysis. So this is kg square, meter square, second to the power minus 2, because the unit of h is joule second, right, which is kg meter square second to the power minus 1. This will be kg meter square. So this is meter to the power 4 actually, the square. So this is kg meter square to the power minus 2, which is the unit of joule. Okay. Again, it is given in terms of electron volts, so we have to do the conversion. First calculate this. So this is 6.024 into 10 to the power minus 18 joule. 18. Okay. So I will do the conversion. So E1 in electron volt. This will be 6.024 into 10 to the power minus 18 joule by 1.6 into 10 to the power minus 19 joule per electron volt. So this is 37.65. Okay, so this is a very large number, like 37.65 electron volt. So the answer here is A. Right? Now, what you can check, like what will be the value if L is 1 nanometer. So let's do that also. So for L equal to 1 nanometer, this is not given in the question, but I just want to do and check. So E1 will be 6.626 into 10 to the power minus 34 square divided by 8 into 9.11 to 10 to the power minus 31 into 10 to the power minus. So this is 10 to the power. So this is 10 to the power minus 9 meter. So this is 10 to the power minus 18. So this will be this is 6.626 024 into 10 to the power minus 20 joule. So you can see that it is two order different compared to zero point 0.1 nanometer thick wall, thick barrier. So in electron volt it will be 1.6 divided by 10 to the power minus. So this is 0.3765. So you can see the difference. If the confinement is more, that means the thickness of the well is less, then the energy levels, actually ground state energy level, goes up. So as I mentioned earlier in one of the question. Okay, now if it is, you can see the difference, 0.1 nanometer, if this energy is very high for L equal to 1 nanometer, this is decreasing, and when L is very large, like maybe hundreds of nanometer, then it will be approximately equal to 0. That means the ground state energy can be 0 for a large system, and the energies will be like continuous. Okay, so if the confinement is very small, so there will be energy levels, these are discrete and quantized, so this the difference is not equal because it depends on n square. Now if it is a very large system, this will decrease and it will seem like the energy levels are continuous. Okay. So that is why we don't need to consider the energy quantization, because most of the problems we deal with in classical systems are like large system. By large means it is maybe larger than 100 nanometer or so, don't know the exact value. But when you consider devices or like any system which are much smaller, then you have to consider the quantum effect. For example, like here in the question it is given, because of the quantization, because of the because it is a quantum mechanical system, the energy levels are quantized. So I hope this question is clear. I had few more questions, but maybe I can discuss later in the next week also. So we discussed some of the problems related to quantum mechanics, and so I hope the problems are clear, and if there is any question you can ask me, or I will stop the session. So what is the due date for this assignment? It's 4/10. Okay. So I'm stop sharing. If there is no question, then I think we can leave. Okay, so thank you everyone. I hope the session was useful. Okay. Do you have any question? Otherwise I will end this session. Your voice is not audible. Okay, it's already time, so I did not see video. Uh, so what videos? Like this week in detail. Okay, let us see. So I'm guessing that you have not completed the videos, right? So you can go through it, and recording of this session will also be available to you. So if you have any question, then you can re-watch it. Like if there is any question, you can ask me, maybe in the discussion forum or in the YouTube comments. So it's up to you. I will try to reply it before the exam, but please give me some time if you have any question. Okay. And if you want to study about this topic, because so only week 11 in this week was quantum mechanics part was covered, so you can refer to any like quantum any solid state device book. The first chapter will be uh, like this basic Schrodinger equation, so you can refer to treatment or any other book. So I don't think there will be problem in understanding. Okay. How to contact you? You can write in the discussion forum in the course, or you can, like if you want, then you can comment in the YouTube videos also. So I'll try to get back to you. Okay. Okay. And fine, I will stop the session.